see a lot of familiar faces in the audience. Thank you very much, IWSA, for giving me this opportunity to give a talk and actually getting to know you. And I hope to be associated in the future as well. So I'll start my talk and right. So can everyone see my slide?
Yes, Sushmita.
Okay. Thank you. Yeah. All right. So today I thought I'll talk to you about most of what I do, spend my time doing and thinking about. But I'll talk about it from a larger perspective today. So I'll talk about dark matter and its role in the evolution of the universe and how we understand it, and sort of to the model of the history of the universe that has come to be known as the standard model of cosmology today, and how we arrived at it, and why we think it is robust, and how we test it. So I often, when I give these talks, I like to start with this image because, as mankind has always been fascinated with the sky, right? For centuries, we have been fascinated with the night sky. And this is a picture here from taken by the Hubble Space Telescope. So Hubble Space Telescope was sort of like the precursor version of IWSA, the images from which you are very familiar now, which has been in the news in the recent times. So this is this is one of the fields from the Hubble Space Telescope. This is a deep field. And what we're looking at here, this is the image of a random location in the sky. And what we're looking at here is this multitude of galaxies. In fact, every bright point in this image corresponds to an individual galaxy. So you can see, spirals to ellipticals and all the beautiful different kinds of galaxies that we have come to know today. While one thing that stands out to you is these galaxies that you're seeing in this image, another thing that actually stands out is that galaxies are actually very special locations in the universe. When we look at a random picture of the night sky, take a deep image of the night sky, so that we can see even the faintest objects. What we come to realize is that while these bright spots are galaxies, a lot of our universe is in fact empty. The galaxies form a very small portion of this entire area that we're looking at. Most of our universe is in fact, most of the regions in our universe is actually a void, and there's actually no galaxies. Galaxies are locations, so our own planet, which is actually a small planet in one of these specks of light in the universe, in one of these galaxies within a solar system, in one of these specks, we are one of these planets, but we happen to be living in a very special place in the universe, which is not actually empty, where actually matter has come together and clustered in a small region in the universe and lit up. And we are living in a region where structure or matter or stuff, in a sense, has come together and formed to light up as stars, to get bound together as a galaxy, and basically appear clustered in the universe. So what I'll talk about today is a lot about how we came to form structure in the universe. How we came to form these guys. In fact, if you look closely, each of these is a single galaxy. But if you look at some of these images, for example, if I focus in and close up in one of them, we actually see that some of these specks are actually not a single galaxy, but actually clusters of galaxies that appear to be bound together. So some of the questions that I think about, and that cosmologists and astrophysicists today are thinking about, is how did the universe come to look the way that it does today, right? Why are the galaxies in the skies distributed in the way that they are? Why do they come in different shapes and sizes, of course? And how do we actually form this network of galaxies in the sky, Why, for example, do the galaxies not appear uniformly distributed? If galaxies were uniformly distributed in the universe, each of our sight line would end on a galaxy, and our night sky would appear uniformly bright in some sense. But that is not the case. Our universe is in fact quite clustered. We have some regions where there's a lot of stuff going on, a lot of matter comes together, but a lot of the other regions are actually relatively empty. And we have this network-like structure in the universe. So even when we look at individual galaxy, and today we've come to understand actually all the stuff that we can actually see, that is all the bright stars and galaxies and black holes and everything, or all the matter that actually can emit light, forms a very small portion, small budget of the total matter that is in the universe. In fact, matter that can light up forms about only 15% of all the total matter that there is in the universe. And by matter, I mean anything that has mass, essentially. Anything that has mass and can interact through gravity is called matter. So you and I and everything, we're all matter, made of matter particles. But the matter that can actually light up and that we can actually see forms only about 15% of the total matter in the universe. Now, this is something that we actually, over the last century or so, have come to understand and come to infer, starting sort of from our investigation of the sky. In fact, looking closely at galaxies around the 1970s, in pioneering work by Vera Rubin at the Lowell Observatory at Flagstaff, Arizona, was the first time that we inferred that matter as we know it, we don't really quite understand the total, where most of the mass in the universe lies. So she was looking in the 1970s at the rotation curves of this galaxy called the Andromeda Galaxy, which is our nearest neighbor. What she was doing is she was looking at this galaxy, and they were measuring the velocity of gas and stars moving away from the center of the galaxy somewhere here to the outskirts of the galaxy. So what they were trying to measure was the circular velocity, that is, the rotation velocity of the stars as they were moving away from the center of the galaxy. Now, what they found, surprisingly, is that what they were expecting is what we see on the left. That is, the velocity of the stars as we move away from the center of the galaxy would increase and then fall off as we move from far away from the galaxy. That is very much what happens in our own solar system. We have the sun, the planets in the outskirts have lower and lower velocities, right? They're rotating around the sun at smaller velocities. So they had expected to find something like our own solar system, but what they found instead is
police complaint.
Yeah. So what we found instead was something that we see on the right. Hi, I think someone's microphone is not muted. Can everyone hear me? Hello?
Yes, we can hear you.
Okay. Yeah. But what they found instead is something that we see on the right, that as we go further out from the center of the galaxy, the stars are actually not slowing down, they're moving pretty fast. In fact, the velocity of the stars sort of becomes constant as we move outside. They don't fall off as we expect in the solar system. Now, this was very confusing because if we accounted for all the mass that if we accounted for all the mass that was, we understand how much mass there is in attached to stars, and we understand how much mass there should be attached with the luminous component. So if we account for that mass, then we can basically use Kepler's law and say what the velocity of stars should be. So it so happened, it seemed that there was somehow much more mass than we could account for in the luminous component of the matter that was basically speeding up the stars in the outskirts of the galaxy. In fact, a hint of this was also there much earlier. In fact, in 1933, Fritz Zwicky, who was a Swiss scientist, he was studying a cluster of galaxies that is very close by to our own galaxy called the Coma cluster. And he was looking at the motion of the galaxies in the Coma cluster. And what he found is that these galaxies are moving really, really fast. And if these galaxies are moving at the speeds at which they are moving, this cluster should not appear bound. It should actually break apart. But what he instead saw is that the Coma cluster, the galaxies appear to be bound to each other and are orbiting each other in some way, as if there was more mass in the system than that was attached to all the galaxies and the stars that we could see in that system. So in fact, he had called something, he had inferred that there might be something like some kind of Dunkel materie or some dark matter that we cannot actually see. So from the dynamics of galaxies, and primarily by the experimental evidence provided by Vera Rubin, by actually measuring the rotation curves of galaxies and the dynamics of galaxies in massive galaxy clusters, and along with that by some simultaneous work by Oestreicher and Peebles, who realized that you cannot actually form thin galaxy disks in the universe without being supported by a massive structure of mass that was spherically distributed around these galaxies. So all these evidence sort of came together to tell us that we are actually not all of the matter in the universe is actually not tied to the stars and the things that light up. In fact, every galaxy we came to understand, and now we know that even better by having measured many, many galaxies and their rotation curves, that every galaxy is in fact surrounded by dark matter. In fact, a dark matter halo, the galaxy itself is actually quite compact and lives sort of at the center of the gravitational potential well that is created by a much larger, puffier mass of matter around it, which, since we cannot see it, we call dark, and it forms a halo around every galaxy. This matter does not emit light. And as we said, the reason we think it's matter is that we can infer its presence by its gravitational influence. So everything that has mass interacts gravitationally, interacts via the force of gravity, the attractive force of gravity. So even though this matter does not actually emit any light in any part of the spectrum that we know of, we know of its presence because of the way it influences the motion of stars and of gas and of clusters of galaxies through the gravitational force. So this was very surprising to us. This was very surprising because matter, as we understand it, in the standard model of particle physics, does interact electromagnetically, does emit light, but this was something very unique, which we could not see, but which was influencing the motion of galaxies. In fact, over the years, over the last many decades, we have inferred the presence of dark matter, this matter that we cannot see, but has gravitational force. In many different ways, we have found multiple different lines of evidence for its existence. Not just, of course, as scientists, we want to, when we find a result, we want to test it, we want to falsify it, we want to understand it. So even though, so there have been many alternative theories to sort of understand the rotation curves of galaxies, but in a sense, the paradigm of dark matter has sort of stood the test of time. So some of the other ways in which we can sort of understand the presence of dark matter and infer its properties, one of the ways is one of the most promising ways and one of the most practiced ways is also through gravitational lensing. which has also provided ample evidence for the existence of dark matter. Now, gravitational lensing is an effect which was predicted by Einstein, and it is from his theory of general relativity, which was basically the theory of gravity. So what that tells us is that anything. So it tells us that that we live, that the web of space and time, so x, y, z, and time, like our spatial and temporal coordinates, that space-time is basically bent by the presence of mass. So if you have any really massive object, it will bend space-time, and light and all matter, including even photons and things that are the carriers of light, they follow curves on these geodesics or basically paths on this space-time, right? And what happens is, if you have a massive object, it bends the space-time, and so it bends the path of every so around this bent space-time. Light essentially follows the geodesics, but because the geodesics themselves sort of get bent around massive objects, the path of light bends around mass. So this is very much like what happens to light when you look at it through a simple lens, right? Which we are all familiar with. But this is happening not because of a different refractive index of spectacle lens or any other lens that we see, but in fact due to the presence of mass in the space-time of the universe. It's very similar to the effect of optical lensing. So because it bends the path of light, this is a video taken from IISER, where you can see that there are these yellow spots, which are basically a cluster of galaxies. And as the cluster of galaxies moving in front of the field of view, it's creating this lensing-like arcs all around it, which are basically the distorted images of objects behind it. So this was an effect which was basically, which would actually end up being one of the most robust tests of Einstein's theory of general relativity, that mass bends space-time, and therefore anything behind a massive object like this cluster of galaxies would appear lensed to us. So this, we see examples of this in many different fields in astrophysics, right? So for example, most recently, you may have seen the image of the black hole. This is actually the image of the black hole in M87. And what it does is, the black hole, being really massive, bends the path of the light coming from the accretion disk and makes this lens-like image. And then you see these lensed images of galaxies around, bright galaxies in the foreground all the time. For example, this is a faraway galaxy, this blue image, and it's being lensed around this elliptical galaxy. Similarly, you must have seen this image from IWSA, where again, you're looking at a cluster field. So you're looking at a field in the sky where there's a massive cluster of galaxies, and that mass essentially bends the path of lights of the galaxies that are behind it from our line of sight, and creates these beautiful arc-like shapes all around it. Now, why I'm saying this is essentially by measuring these arcs and by measuring how much these galaxies, how much bending, how much distortion there is in the background galaxies, that essentially depends on how much mass there is between that background galaxy and us. So that is another way of essentially probing, even though we cannot see mass, that is another way of sort of probing the presence of mass between us, between the line of sight, in the line of sight between us and some distant galaxy, for example. So through gravitational lensing also, we saw that we could not actually explain the total amount of distortion that we were seeing simply by adding up the mass in stars, that we always needed more and more mass than what we could see in this luminous matter. And we needed in fact, many orders of magnitude more mass to explain the bending of light around these images that we see. So that provided some independent evidence for the presence of dark matter in the universe, right? Apart from just, apart from the fact that that this matter, so we want to understand what is the property of this matter, right? We want to understand what are the basic microphysical properties of dark matter. So, so apart from the fact that we know that it does not seem to emit light, and that it interacts gravitationally, gravitational lensing of this particular system called the bullet cluster system actually provided is a pioneering work, but which actually tells us that not only does dark matter not interact through electromagnetism, does not emit light, interacts only gravitationally, it actually told us dark matter is collisionless. Unlike gas, which is collisional and can interact through hydrodynamic forces, has pressure and so on, pressure and temperature, we found that dark matter is in fact collisionless. So this, what we are looking at here, is the bullet cluster system. So what is the bullet cluster system? It's basically two massive clusters of galaxies. So there was that are passing through each other. So there's a cluster of galaxy that is bound. There are two clusters of galaxies that are bound independently, and then they are ramming into each other and passing through each other. So this is a smaller cluster and this is a larger cluster. And what they found is when they looked at this image of these two merging clusters, what they found is that the gas, which is collisional, which can exchange energy through collisions, through hydrodynamic collisions, essentially shocked and sort of stayed near, interacted with each other and sort of stayed near the region where the clusters pass from each other. So they sort of lagged behind the galaxies which sort of smoothly pass through each other. But what they found is that the matter, and this they found through lensing, that the center of mass of the matter is actually significantly separated from each other. So what they found is that when these two clusters of galaxy merged and sort of passed through each other, the mass passed through smoothly, but the gas, which can interact with each other through collisional forces, stayed behind and lagged behind and trailed behind, whereas the dark matter simply passed through each other. So this blue is where the dark matter is, and this pink is where the gas dragged behind and stayed behind. So this essentially showed us that not only did this help us infer the presence at the center of mass of the matter, the total mass was actually quite separated from where the gas was, but also the fact that dark matter can actually pass through each other in a sense collisionlessly, and only interacting sort of through gravitational scattering, but no other effects essentially. So this, from lensing through dynamics of galaxies, through basically these kind of merging systems, and also through something else that I will briefly get into later, through the through the cosmic microwave background. Over the years and over the decades, we have actually found multiple independent lines of evidence for the existence of dark matter. And even though we know even though we don't really know what exactly the properties of this matter is, and we are trying essentially going ahead to design experiments and design questions and work out the theory of what this matter, what are the exact microphysical properties of this type of matter. We definitely know that it exists. In fact, it's sort of conspicuous in its absence that we don't see it, but we know of it through all of its gravitational effect that it has on other galaxies and other galaxies, gas, and everything that we can in fact see in the universe. Right. So today what we have is the cold dark matter paradigm. We think that dark matter is a massive particle which interacts gravitationally. So anything that is massive will have gravitationally. We also think that it is non-relativistic and cold. And we think that it apart from gravitation, it has no interaction, and it is in a sense, it is collisionless. And most of the dark matter that we know actually exists in the form of dark matter halos, which are these bound structures which surround galaxies, bound nearly spherical structures which sort of surround our galaxies and overtly dominate the total mass budget of the region of a galaxy. Right. So over the last many decades, what we have come to know that the standard model of elementary particles. So this is what particle physicists study, and this is the standard model of elementary particles, of the things that we know and are familiar with, everything that emits light and so on. And we also have a model, a very promising model for understanding the elementary particles that make up matter as we know it. The standard model currently does not explain what dark matter is. So we actually need extensions to the standard model to understand what dark matter is and what its properties are. And all of these galaxies and stars and all of these things that we know and love, our own lives and our life on Earth and all of the people and everything from the smallest scales to everything on the largest scales like galaxies and stars, we know today actually forms only a really small, a fairly small percent of the total energy budget of the universe. So all of this, all of the known matter can be packed into only about 4% of the total energy budget of the universe. So we call this the energy density of the universe. So this is the general Einstein's field equation, which tells us about, the evolution of our universe and the evolution of space-time. And the energy density has about 4% baryons, or matter, standard model matter has about 23% dark matter. So and together they form all of matter in the universe. And actually 73% of the energy budget, the energy density of the universe, these are different components. If we ask what is the energy density in a region composed of, 73% of it is actually something completely different, is a completely different thing that we're not going to get into today. It's in fact what we have now come to call dark energy. So even dark matter is in fact a small 23% of that. And baryons are an even smaller fraction of the baryons, or which I will use interchangeably with standard matter, form a really small percent of the universe. So just briefly going into why at all did we even introduce this idea of dark energy? And no talk of cosmology is complete without mentioning one of the most important pillars of cosmology. Why did we need to invoke dark energy and what it is? Essentially, we know that we've known for a while that our universe is actually expanding, in the sense that we know that galaxies are receding away from us at a certain velocity. And every point in the universe is sort of receding away from each other at a certain velocity. But around the 1990s and 2000s, what we learned is not only is the universe expanding, the universe is in fact in a phase of accelerated expansion. And by the universe, I mean that the space-time of the universe is in a state of accelerated expansion, and the galaxies are not only getting away from us at certain speed, they're actually getting away from us at a faster and faster speed with time. And what we think drives this expansion is this component called dark energy. And what we actually found is that how we actually found this is that we measured how much light supernovae give out, and measured supernovae at distant galaxies, and we know exactly theoretically how much light they should give out. And we measured their light coming from distant galaxies, and we found that to match the light and to match the fading of luminosity when some standard candle is emitting light from far away, we found that we need to actually invoke the model of an acceleratedly expanding universe. So dark energy is essentially driving this expansion. And dark matter, which is gravitational, is actually working to do something opposite of expansion, which is since it gravitates, it attracts matter and therefore pulls things towards each other, right? So currently, what we think and what we have learned from observations and also from corresponding theory is that our universe, the essential story of our universe can be sort of, at least from the time that we have structure, can be thought of sort of a balancing act or a tug of war between dark matter and dark energy. So dark matter basically is gravitational, has mass and has gravity, and therefore it sources gravitation. It sources a gravitational potential. Well, it's attractive. It tries to pull everything towards itself. So if a mass will pull other mass towards itself, whereas dark energy is essentially stretching space-time, right? So it's pushing things further and further away from each other. So since both of these things coexist, the structure that we see in the universe and the arrangement of structure in the universe is essentially a combination of these two effects of gravity in an expanding universe, right? Of course, given what the initial conditions of the universe were, we can sort of determine what the entire evolution of the universe should look like, and what we expect to see, which we can go and compare with data. So briefly, what were the initial conditions of the universe? So far we've been talking about dark matter halos. So that's a very local picture. And that is a region in the universe where dark matter basically collected, created a gravitational well, pulled in all the gas, and the gas fell to the center because it can radiate away heat and light, and basically lose energy and fall to the center of the potential well. But initially, in fact, initially what the universe, all of this started essentially as a density field of dark, as basically, if you take the volume of the universe, what we had initially were very small, was more or less uniform with very small perturbations in the different energy components of the universe. So we had, and that picture we've come to learn from what is known as the cosmic microwave background. So that was sort of like the earliest picture of the universe that we took from the photons that are coming from 13 billion light years away, which was a long time ago. And we have been able to make sort of a map of the universe, what it looked like sort of around 13 billion years ago. And we know that the universe was basically a volume which was more or less uniform, but there were small fluctuations of matter or dark matter, radiation, and all different energy components in different locations in space. And wherever there was a small perturbation of matter, because there was a little bit of extra dark matter in some small region of the universe, and because it can gravitate, that region of the universe sort of gravitated and grew and brought in more and more matter around itself and created regions where galaxies lit up, where gas fell in, and etc. So this is essentially a picture, in a sense, of the universe when it was sort of, the universe is today 13 gigayears or 13 billion years old. So this is the time. And at around 0.05 gigayears, so very early time, this is what the density of, say, dark matter looked like in the universe. So there were regions, it was more or less on average uniform, but there were these small regions where there was a little bit of more matter than, say, in this dark region. And this is a simulation of the universe. So with time, what happened is that you'll see that the brighter regions get brighter and brighter with time. And what is happening here is just that the dark matter is just accreting away more and more matter around it. So it's pulling towards itself more matter, and it's getting more and more dense. More and more density of matter in that region is increasing. The rotation is artificial. It's just the way we are showing. And over time, what we get is this network in the universe, this network where the regions that were empty, that had a little less density than the mean density of the universe, have sort of emptied out. whereas the regions which had a little more density in dark matter have become more and more matter rich in a sense. So these regions, these nodes are essentially where galaxies form, where there's a lot of dark matter, there's going to be a lot of gas, and that gas is eventually going to cool down and form stars and light up as stars. So essentially clump together and light up as stars. So essentially what we get, essentially where we are living are these small nodes in the universe. Each of these is a dark matter halo. If I let the movie play on, you will see that I can zoom into one of these nodes, and that node is itself a dark matter halo, and at the center of it, a galaxy will form. And in fact, at the center of each of these nodes, galaxies will essentially form. Okay, so I will maybe go on for a little more time and then maybe take questions in another 5 minutes. So what we start off is a picture of the universe at early time. This was small perturbations in the cosmic microwave background. And we end up with this node of galaxies which grow through time, through gravity, at the same time in an expanding universe. So only regions that have enough matter are able to collapse and form galaxies. And most of the matter in these empty regions are driven out to fall into those overdensities of matter. So this is a simple picture of the history of the universe. We start off with the cosmic microwave background with small fluctuations in the matter density of the universe. And eventually with time, we essentially form structure. And this is where we are today. And at only about 4 million years after the universe was formed, we started to form the first stars. And slowly, we have evolved after 13 billion years to see all these different multitudes of galaxies and so on. Just for some context, while I keep saying that the universe is 13.7 gigayears old, we have many different lines of evidence. For example, now IWSA is looking at some of the oldest galaxies in the universe, and this particular one is one that was created fairly early, nearly at around 12-ish gigayears back or so. And we are actually just starting to see these galaxies using IWSA, and that it's a really fascinating time for cosmology. All right, so go ahead. In the last few minutes, I'll just give a brief review of what is it exactly that I do. So I personally study dark matter halos. These regions of excess dark matter is what I like to understand, spend my time understanding. We understand the basic properties like gravitation and their collisionless nature. And what I try to study is how these self-bound sort of massive structures form. How they form out of these small perturbations in matter density, how they evolve through time. What is the distribution of density of dark matter inside these halos? For example, if I were to measure up how much dark matter there is as a function of distance from the center of the Milky Way, I would get a very specific distribution. And I try to understand theoretically where that distribution comes from, what are the properties of dark matter that lead to that distribution, and many other questions that are related to that. And more importantly, and because as a theorist, we always want to make predictions that can be tested. We also want to see if the actual observed distribution of dark matter in halos actually match with our theoretical predictions based on what we actually understand about dark matter. So I study a lot about the structure, the shape of these halos, and how they affect the evolution of galaxies through time. And underlying all of this is, of course, the basic questions of what is dark matter really, what kind of particle is it, what its mass is, What kind of interactions does it have other than gravity? Does it have any really weak interactions with any other kind of particles that we're not being able to see because the interactions are so weak? And those are the types of questions that we try to answer and design sort of ideas to test the different properties of dark matter. These halos are essentially the densest regions of dark matter in the universe. So if there was some interactions among them, these halos are the region where we would actually start to see them because they're so dense and are so likely to meet each other and other baryonic particles. So the smallest halos sort of hold galaxies like dwarf galaxies, really faint, flimsy galaxies with very few stars, which we can now observe. And the largest dark matter halos actually will hold not just a single galaxy, but actually clusters of galaxies that will sort of orbit each other and appear sort of gravitationally bound to each other. So I particularly focus on the rightmost end on understanding the dynamics of these galaxies and these halos and what we can infer about the dark matter properties by studying them. And also different kinds of things, like we think dark matter is cold. If dark matter was cold in the sense that it didn't have a lot of temperature, it was not sort of jumping around. So this is cold dark matter, very well behaved, very uniform. It would actually fall into the weakest potential wells and form really, really small dark matter halos. So this would be a dark matter halo in the cold dark matter universe. But if dark matter was sort of particles were warm, that they had some temperature, they had a lot of random energy, they would actually oftentimes escape out of the smallest potential wells. And while you would form large halos, you would not form small structures. So this is a cold dark matter halo, and this is a warm dark matter halo. You see a lot more speckles in the left one than in the right one. And these are the sort of questions that we try to answer. In fact, one of the ways to understand the nature of dark matter particles is to look for the smallest halos, just so that we can understand if dark matter has some kind of temperature or some kind of interaction that it escapes away from the smallest object that we find. Right. So I will not go into a lot of the details. Of course, what we do is we understand today that the formation of a halo is basically the gravitational collapse of cold dark matter in an expanding universe. And what I try to do on a day-to-day basis is sort of try to tweak around with each of these assumptions. What if we change the nature of gravity? How would that affect structure? What if we change the nature of dark matter as we understand it? How would that change our observations? What if we change the nature of expansion in the universe? And how would that change our expectations? And finally, I work with observers in the dark energy survey to study. So this is a telescope in Chile, in America, and they observe these clusters of galaxies directly. And I use their data to infer various properties of these objects. Okay, I'll just come to the close. I should say that, backed by theory and also, world-leading sort of experiments and beautiful experiments that, scientists, in fact, from all over the world have come together to create, we can now really start to ask the integrities of what dark matter particles are and try to really constrain the microphysical properties of these objects. Currently, the Gaia mission is mapping out, the Gaia satellite, which is a space mission, is mapping out our own Milky Way's dark matter halo. JWST is going to give us an unprecedented view of the young universe, and the Vera Rubin Observatory, which is actually coming up, it will basically map out the galaxies in about half the sky. So there are many different directions from which we are, trying to attack the problem of dark matter and dark energy and trying to get to answers. And finally, I think I'll end with saying that the dark matter paradigm has been one of the most promising and robust pillars in modern history, and it has actually been tested extensively, and it has, in a sense, stood the test of time. We still understand little of what it actually is. And the hope is that in the future, we will have the data and the theoretical understanding and the simulation and bringing in all of our minds together, we'll be able to solve this problem of dark matter and sort of understand what our universe is made of. Okay, so I'll end there. I'll leave my email address for those of you who have questions, and I'll take questions from everyone now. Thank you.
Thank you, Dr. Sushmita. You have given more questions than what we expected. My first question is very, very humble and simple. Is there a difference between the cold dark matter and the hard dark matter?
Yes.
And how do you differentiate